Next chapter, the mole. Now, while studying chemistry, it is not just enough to know what reagents to react to form what products. It is equally important to know how much of each reagent to use to produce what quantity of the product. We know that chemical reactions involve atoms, either free or combined into compounds. A chemical reaction may involve elements combining to form a compound breaking down into two or more products, an element replacing another in a compound to give at least two new products, and so on and so on. When we write chemical equations, they only give a simplified ratio in which atoms combine. An equation like this one only shows 2 atoms of magnesium and 2 atoms of oxygen. But chemical reactions involve millions and millions of atoms, molecules and compounds. Consider a reaction between iron filings and sulfur to form iron 2 sulfide. The equation shows a single case for 1 iron atom and 1 sulfur atom. But atoms are very small in size, so 1 teaspoon of sulfur powder contains millions of sulfur atoms. And because we cannot count these atoms, we use mole to represent a certain number of atoms, molecules, or other particles in chemistry. So, what is a mole? A mole is simply a specific number. In life, we might ask for 12 or a dozen of eggs, or a pair of socks for 2, or a ream of 500 sheets of paper. A mole is exactly the same. It's just a number, and it's precisely 6.02 times 10 to power 23. So we could have a mole of eggs, a mole of socks, or even a mole of sheets of paper. In chemistry, however, we use it to represent atoms, molecules, compounds, and other particles. This is because atoms are very small. It's just a convenient term to represent massive numbers. A mole is a massive number, 6.02 with another 21 zeros after it. This number was first described by Amedeo Avogadro, an Italian scientist. It represents the number of particles in 1 mole of a substance, and these particles could be atoms, molecules, ions, electrons, and so on. It is called the Avogadro's number, or the Avogadro's constant, L equal to 6.02 times 10 to power 23 particles per mole. So you see, a mole is a very large number, and the reason is because atoms are incredibly small. In half a liter bottle of water, there will be just over 25 moles of water molecules. We can therefore work out the number of molecules of water in that bottle. Remember, 1 mole contains 6.02 times 10 to power 23 molecules of water. So it's 25 times 6.02 times 10 to power 23, giving us 1.505 times 10 to power 25 molecules. And so you can see the reason why we use moles. It is a convenient way to quantify huge numbers. It is easier to talk about 2 moles of sodium rather than 1.204 times 10 to power 24 atoms of sodium. And it's easier to mention half a mole of water rather than 3.01 times 10 to power 23 molecules of water. So what exactly does 1 mole of atoms or molecules weigh? Well, this depends on just how big the atoms are. Just because we have the same number of atoms in 1 mole, it does not mean they are all the same size. For instance, you're probably aware that a hydrogen atom is much smaller than a gold atom. So 1 mole of gold will weigh much more than 1 mole of hydrogen, just in the same way that a dozen of eggs will weigh more than a dozen grains of rice. We'll look at this in molar mass next. atomic number, and mass number. When you look at the periodic table, you see that each element has its own box, and within that box you will find two numbers: the atomic number or the proton number and the mass number. The atomic number has symbol Z. This number tells us how many protons are in one atom of that element. The number is always the same for all atoms of a particular element. Atoms of different elements have different atomic numbers, meaning they have different number of protons. So an atom of hydrogen has atomic number 1 because it has one proton. An atom of oxygen has atomic number 8 because it has 8 protons. The next number is the mass number. It has a symbol A. It tells us how many protons and neutrons are present in one atom of an element. We know that a proton and a neutron has each a relative mass of 1, and that electrons are so small that their mass is negligible. So the mass of an atom is basically due to the mass of protons and neutrons in that atom. The molar mass of a substance is the mass in grams of 1 mole of that substance. It has units grams per mole. For any element, molar mass is equal to the relative atomic mass of that element expressed in grams. Sulfur has mass number 32. That means 1 mole of sulfur atoms will weigh 32 grams. Recall also that 1 mole of a substance contains 6.02 times 10 to power 23 particles. So it's also right to say that 6.02 times 10 to power 23 atoms of sulfur will weigh 32 grams. Also, 6.02 times 10 to power 23 atoms of iron is equal to 1 mole and will weigh 56 grams. For carbon, 1 mole is equal to 6.02 times 10 to power 23 atoms, which is equal to 12 grams, because carbon has mass number 12. So the molar mass of sulfur is 32 grams per mole. The molar mass for iron is 56 grams per mole, and carbon has molar mass 12 grams per mole. So we can say for atoms, the mass of the Avogadro number of particles is equal to the relative atomic mass in grams. Therefore, the mass of Avogadro's number of hydrogen atoms is 1 gram. The molar mass is 1 gram per mole. The mass of Avogadro's number of chlorine atoms is 35.5 grams. The molar mass of chlorine is 35.5 grams per mole. For molecules, the mass of Avogadro's number of particles is equal to their relative molecular mass in grams. So the mass of Avogadro's number of hydrogen molecules is 2 grams, and the molar mass is 2 grams per mole. The mass of Avogadro's number of chlorine molecules is 71 grams, and the molar mass is therefore 71 grams per mole. If someone asks you, what is the mass of Avogadro's number of chlorine particles? It is impossible to answer the question without the person going into further details. If by chlorine particles they meant atoms, the answer is 35.5. If however by particles they meant chlorine molecules, the answer is 71 grams. When we compare chemicals, we compare equal number of particles even though the weights are different. So if we have compounds instead of atoms, it doesn't matter how many atoms are in the formula, only the number of compound particles. Let's say you have 1 mole of iron atoms, but they are in a compound iron 3 chloride. This means you also have 1 mole of the compound. It's easy to see this Because if you have 6.023 times 10 to power 23 particles of iron 3 chloride, then it means you also have 6.02 times 10 to power 23 atoms of iron. The ratio of iron to iron 3 chloride is 1. What about chlorine atoms? The ratio is 3 to 1. There are 3 chlorine atoms per formula unit. For every mole of iron 3 chloride, there are 3 moles of chlorine atoms. So if you had 6.02 times 10 to power 23 particles of iron 3 chloride, then there will be 3 times 6.02 times 10 to power 23 chlorine atoms. For ionic compounds, the molar mass is the sum of the relative atomic masses of individual elements constituting the compound. So 1 mole of iron 3 chloride, which is equal to 6.02 times 10 to power 23 particles of iron 3 chloride, will weigh 162.5 grams. This is called the relative formula mass. The molar mass is therefore 162.5 grams per mole. What if we had iron 3 oxide? For 1 mole of iron, we have half a mole of the compound because there are 2 atoms of iron for every 1 particle of the compound. 1 divided by 2 is equal to a half. You can have half a mole of anything or even a quarter because a mole is really a very big number. This number can be broken down into smaller numbers, so it's okay to have fractions of moles. You can also double them to say that for 2 moles of iron, you have 1 mole of the compound. This is okay too, because the numbers are relative. How about oxygen? How many moles would you have? The answer is 3 moles for every mole of iron 3 oxide. Now for some calculations, we do some simple conversions. Example 1. How many atoms are there in 0.2 moles of magnesium? Remember, the Avogadro's number is 6.02 times 10 to the power 23 particles per mole. Therefore, 1 mole of magnesium will contain 6.02 times 10 to the power 23 atoms. The question is, 0.2 moles of the same magnesium will contain how many atoms? We have 0.2 moles over 1 mole times 6.02 times 10 to the power 23 atoms. The moles cancel out and we have 1.204 times 10 to the power 23 atoms. Example 2. How many atoms are there in 0.4 moles of nitrogen molecules? Again, the Avogadro's number is 6.02 times 10 to the power 23 particles per mole. 1 mole of nitrogen will contain 6.02 times 10 to the power 23 molecules. The question is, 0.4 moles of the same nitrogen will contain how many molecules? So 0.4 moles over 1 mole times 6.02 times 10 to the power 23 molecules. That gives us 2.0408 times 10 to the power 23 molecules. But remember, 1 molecule of nitrogen contains 2 atoms. Nitrogen is a diatomic molecule, and so we shall have 2 times 2.0408 times 10 to the power 23, and we get 4.0816 times 10 to the power 23 atoms of nitrogen. Another example. What is the mass of 1.806 times 10 to the power 24 atoms of calcium. Now we know the relative atomic mass of calcium is 40. Therefore, the molar mass of calcium is 40 grams per mole. So 40 grams of calcium contains 6.02 times 10 to power 23 atoms of calcium. The question is, 1.806 times 10 to power 24 atoms of calcium will weigh how much? So we have 40 grams times 1.806 times 10 to power 24 over 6.02 times 10 to power 23. Atoms cancel out and we get 120 grams. Now we do mass to moles conversion. We have seen that molar mass is the mass of 1 mole of a substance. This is equal to the relative atomic mass of an element, the relative formula mass of an ionic compound, and the relative molecular mass of a molecular compound. Therefore, the number of moles is equal to mass in grams over the molar mass. For example, how many moles are in 2.84 grams of sodium sulfate? And you are given the relative atomic masses of sodium, sulfur, and oxygen. For sodium sulfate, the relative formula mass will be given by 23 times 2, there are 2 atoms of sodium in that formula, plus 32, the relative atomic mass of sulfur, plus 16 times 4, the relative atomic mass of 4 oxygen atoms, and that gives us 142. Therefore, the molar mass of sodium sulfate is 142 grams per mole. Number of moles will be equal to 2.84 over 142, giving us 0.02 moles. Final example. What is the mass of 0.02 moles of copper 2 oxide? And you are given the relative atomic masses of copper and oxygen. For copper 2 oxide, the relative formula mass will be 64 plus 16, giving us 80. Therefore, the molar mass is 80 grams per mole. Number of moles is given by mass over the molar mass. Doing our cross multiplication, it means mass is equal to the number of moles times the molar mass. In our case, that will be 0.02 times 80, giving us 1.6 grams. Next item, empirical and the molecular formulae. Now, an empirical formula is the formula that indicates the number and types of atoms in a compound in the lowest ratio. A molecular formula, on the other hand, is the formula that indicates the actual number and types of atoms in a molecule. The empirical formula can always be determined from the molecular formula, but the reverse is not possible. Let's say you have a compound that is 54.52% carbon, 9.17% hydrogen, and 36.31% oxygen. We determine the empirical formula. Now, the first step is to assume that you have a 100 grams sample. You can actually assume that you have any mass of a sample, but because percentage means 100, it's easier to use 100 gram sample because the respective percentage can be assumed to reflect the same mass. Consequently, out of the 100 gram sample, 54.52 grams will be carbon, 9.17 grams is hydrogen, and 36.31 grams is oxygen. Next step is to convert the number of grams into moles, and we do this using the molar mass. Remember, the number of moles is equal to mass over the molar mass. For carbon, we shall have 54.52 divided by 12 the molar mass. That will give us 4.54 moles. For hydrogen, we shall have 9.17 divided by 1, giving us 9.17 moles. For oxygen, we shall have 36.31 over 16, giving us 2.27 moles. So we have this mole ratio for carbon, hydrogen and oxygen. But we cannot write a formula with decimal figures. We must convert them into the simplest whole number ratio. We do this by dividing all the moles by the smallest of them. In this case, it will be 2.27. If we do this, it will give us the ratio of 2 to 4 to 1. This is the simplest possible ratio. And so the empirical formula of the compound is C2H4O. Now, what if we were asked to find the molecular formula? Now, we cannot do that unless we are given the relative formula mass of the compound. Assuming we are given the relative molecular mass of the compound as 88, it means the total mass of the constituent atoms in the compound add up to 88 in the corresponding ratios. We are given the relative atomic masses of the elements. So we equate the formula to the molar mass. So we shall have C2H4O times N will give us 88. The relative atomic mass of carbon is 12, so we have 12 times 2, plus relative atomic mass of hydrogen is 1, and we have 4 hydrogen, 1 times 4, plus 16 times N will give us 88. That gives us 44, N is equal to 88, and N is 2. And therefore the formula will be C2H4O times 2, which becomes C4H8O2. Another example. Oxalic acid contains 26.68% carbon, 2.24% hydrogen, and 7.08% oxygen by mass, and has a molecular mass of 90. Give the empirical and the molecular formula. Now we assume we have a 100 grams sample. We convert the percentages to the corresponding masses. Carbon is 26.68 grams, hydrogen 2.24 grams, and oxygen 71.08. Convert the mass to moles by dividing by the respective relative atomic masses. Carbon 26.68 over 12 will give us 2.22. Hydrogen 2.24 grams over 1 will give us 2.24 moles. Oxygen 71.08 divided by 16 will give us 4.4 moles. Now we obtain a whole number ratio for the moles. We divide by the smallest, that is 2.22 moles. So for carbon, 2.22 divided by 2.22 is 1. Oxygen, 2.24 divided by 2.22 is roughly 1. And for oxygen, 4.44 divided by 2.22 is 2. Therefore, the empirical formula is CHO2. For the molecular formula, we know that the relative molecular mass is 90. So we have CHO2 times N is 90. 12 plus 1 plus 16 times 2 times N is 90. 45 N is 90 and N is 2. Therefore, the molecular formula is C2H2O4. Next item, percentage by mass. Now, usually, chemical compounds are written using chemical formula. This tells us how many atoms there are of each element. Water is H2O. This means there are 2 atoms of hydrogen for every atom of oxygen. We can calculate the percentage by mass of each element, hydrogen and oxygen, in a water molecule. To do this, we need to know the atomic mass of each element so we can calculate the total mass of a water molecule. For water, we use the atomic masses of hydrogen and oxygen. Let us calculate the total mass of 1 mole of a water molecule. There are 2 hydrogen atoms, each with atomic mass of 1 gram. So 2 times 1 is 2. Then we add this to the atomic mass of 1 oxygen atom, which is 16 grams. So 16 plus 2 is 18 grams. This is the molar mass of water, 18 grams per mole. Now that we know the molar mass of a water molecule, we can work out the percentage by mass of hydrogen and the percentage mass of oxygen. Percentage means out of 100. So we use the formula mass percentage is equal to mass of the element present in 1 mole of a compound divided by mass of 1 mole of that compound times 100. Let's start with hydrogen. The mass of hydrogen present was 2 grams. If you divide that by 18 and multiply by 100, we get the percentage mass of hydrogen present in water. That is 11.1%. And you can work out the same for oxygen, but it's not necessary because the remaining percentage is actually that of oxygen. So we do 100 minus 11.1, giving us 88.9. Next, concentration of solutions. Now, the concentration of a solution is a measure of the number of particles of a solute, a dissolvable solid, which are in a solvent, a dissolving liquid. How would you compare the number of particles in a concentrated solution to a dilute solution? The number of particles in a concentrated solution is greater than the number of particles found in a dilute solution. Think about sweetening a drink by adding sugar. The more sugar you add, the sweeter the drink tastes. Concentration can be given using 2 units and accompanying formula triangles. The first formula for calculating concentration is moles of solute per unit volume of the solution. Here we divide moles over volume. Here is the formula triangle. Most of the times, volumes are measured in cubic centimeters. 1,000 cubic centimeters is equal to 1 cubic decimeter, which is equal to 1 liter. So how many cubic decimeters is 500 cubic centimeters? To get the answer, we divide 500 cubic centimeters by 1,000 cubic centimeters. So 500 cubic centimeters is the same as 0.5 cubic decimeters. You can find any of these quantities by covering the one you are looking for. For example, to find moles, you multiply concentration by volume. To find concentration, you divide number of moles by the volume. If you have 2 moles of salt and dissolve in 2 liters of water, we can calculate the concentration of the solution. 2 moles divided by 2 liters will give us 1 mole per liter, or 1 mole per cubic decimeter. The second way of representing concentration is very similar, except that we use mass of the substance per unit volume. The formula is mass over volume and has units grams per cubic decimeters. The formula triangle is the same. For example, If you want to make a solution of 10 grams per cubic decimeter with a volume of 250 cubic centimeters, what mass of salt will you need to dissolve? The first thing to do is convert 250 cubic centimeters into cubic decimeters. How? By dividing by 1,000. So 250 over 1,000 gives us 0.25 cubic decimeters. 10 grams per cubic decimeter means 10 grams are contained in 1 cubic decimeter. But we have 0.25 cubic decimeters. How many grams? We have 10 grams times 0.25 cubic decimeters over 1 cubic decimeter. Cubic decimeters cancel out and we remain with 2.5 grams. That is the mass of salt that you need to dissolve in 250 cubic centimeters to make a solution with a concentration of 10 grams per cubic decimeter. Now we look at molarity and molar solutions. Let us now differentiate molarity and concentration. When you consider these two terms, you need to be thinking about solutions because both of them describe just how much a dissolvable substance, that is a solute, is present in the liquid it's dissolved, that is the solvent. A lot of people, including scientists who should know better, tend to use the terms molarity and concentration interchangeably, and this is a bit of a misnomer. The difference is down to the units. When we talk about the molarity of a solution, we mean the number of moles of a solute per cubic decimeter of a solution. The units are moles per cubic decimeter or molar. Remember, 1 cubic decimeter is equal to 1 liter. Concentration, on the other hand, can be written in these units, but there are other units of concentration. And therefore, concentration is a general term used to describe the amount of substance dissolved per unit volume of a solution. And molarity is just one way of expressing concentration. Molarity is given by moles of a solute dissolved divided by volume of the solution. Take note of the statement volume of solution because it will mean something later. Consider 0.2 moles of silver nitrate dissolved in 0.075 cubic decimeters of water. What is the molarity? Molarity will be given by 0.25 over 0.075, giving us 3.3 moles per decimeter cube. The units moles per decimeter cube is molar, and that is the molarity of the solution. (0.0100 moles of oxalic acid added to 100 cubic centimeters of water. You can work out the molarity using the 100 cubic centimeters or first convert the volume to cubic decimeters. Just remember, 1,000 cubic centimeters is 1 cubic decimeter. If you want to work with cubic decimeters, first divide the volume by 1,000. So we divide 100 over 1,000 and we get 0.100 cubic decimeters. Then molarity will be equal to 0.0100 moles over 0.100 cubic decimeters. That gives us 0.100 moles per cubic decimeter, which is 0.1 molar. But you can still work with cubic centimeters. Molarity is also equal to moles per 1,000 cubic centimeters. Why? Because 1,000 cubic centimeters is equal to 1 cubic decimeter. So in our solution, 0.0100 moles are contained in 100 cubic centimeters. How many moles will be in 1,000 cubic centimeters of the same solution? We have 0.0100 moles times 1,000 cubic centimeters over 100 cubic centimeters. The cubic centimeters cancel out and we remain with 0.100 moles. And because these moles are contained in 1,000 cubic centimeters, this is the same as 0.1 molar. Now, in almost all cases, however, we only have chemicals in terms of mass, but still we can find the molarity. Consider 0.0748 grams of sodium bromide salt dissolved in 25 cubic centimeters of water. What is the molarity? We simply convert the mass into moles and we use the periodic table to find the molar mass of sodium bromide. Molar mass of sodium bromide is equal to 23 plus 79, giving us 102 grams per mole. Therefore, the number of moles will be equal to 0.0748 over 102. That gives us 7.33 times 10 raised to power negative 4. Next, we convert 25 cubic centimeters into cubic decimeters. We divide by 1,000, and that gives us 0.0250 cubic decimeters. Molarity will therefore be given by 7.33 times 10 to power negative 4 moles over 0.0250 cubic decimeters. And that gives us 2.93 times 10 to power negative 2 moles per cubic decimeter, or molar. Alternatively, we could work with cubic centimeters without converting the volume into cubic decimeters. We had 7.33 times 10 to power negative 4 moles, and these moles are contained in 25 cubic centimeters. What if we had 1,000 cubic centimeters of the same solution? How many moles will it contain? We have 7.33 times 10 to power negative 4 times 1,000 cubic centimeters over 25 cubic centimeters. Cubic centimeters cancel out and we remain with the same 2.93 times 10 to power negative 2 molar. But why is the knowledge of moles so important? Well, imagine yourself a chemist and you work in a chemical plant. A client has ordered 100 kilograms of copper 2 sulfate crystals. To make this, you need to dissolve copper 2 oxide in hot sulfuric acid. This will produce copper 2 sulfate solution from which you can get the blue hydrated copper 2 sulfate crystals. Here's the problem though. How do you know what mass of copper 2 oxide to react with the acid? If you use too much, not all the solid will react, and you will have to spend time separating the undissolved solid from the solution. Too little and you will simply not produce enough product for the client, and you will fall behind schedule. Either way, you could be in trouble. But with the help of moles and the simple conversion formula, problems like this one are easy to solve. The first thing to do is to write the chemical equation and balance it. Fortunately, this one is not hard. All we need to do is change the mole ratio of water from 1 to 4. For the other species, the ratio is 1. Now you know that for every 1 mole of copper 2 oxide, we get 1 mole of copper 2 sulfate. 100 kilograms or 100,000 grams of copper 2 sulfate are required. We now find how many moles this mass represents. Number of moles is equal to the desired mass, that is 100,000 grams, divided by the relative formula mass of the product we want, that is copper 2 sulfate. Using the periodic table, you can work out that this is 63.5 for copper, plus 32 for sulfur, plus 9 times 16 for oxygen, and 10 times 1 for hydrogen, giving us 249.5 grams per mole. That is the molar mass of copper 2 sulfate. Number of moles is 100,000 divided by 249.5, giving us 400.8 moles. This is the number of moles of copper 2 oxide we need to add to the acid. The mole ratio is 1:1, that is copper 2 oxide to copper 2 sulfate ratio is 1:1. And therefore, we need the same number of moles of copper 2 oxide to react with the acid. We now convert it back to mass. Again, this is straightforward. We use the formula. This time, we know the number of moles, 400.8, and we can get the formula mass of copper 2 oxide. 63.5 plus 16 will give us 79.5 grams per mole. To find the mass, only a simple rearrangement is needed. 400.8 times 79.5 will give us 31,860 grams, the mass of copper 2 oxide that you need. Now let's look at this one. In this beaker, we put 2 cubic decimeters of water and add 4 moles of sulfuric acid. What is the molarity? We have 4 moles divided by 2 cubic decimeters. That gives us 2 moles per cubic decimeters, which is equal to 2 molar. Simple, right? Wrong. Remember, in the definition of molarity, we said it's the number of moles per unit volume of the solution and not the solvent. You need to realize that sulfuric acid is also a liquid, and if we add it to 2 cubic decimeters of water, surely the final volume will increase by the amount of the acid. So if we assume that the final solution will have a volume of 2 cubic decimeters, then that is not true. However, when solids are dissolved in a solvent, they don't alter the volume. What is the molarity of a solution formed when 6.75 grams of sodium chloride are dissolved in 452 milliliters of water? Molar mass of sodium chloride is equal to 23 plus 35.5, giving us 58.5 grams per mole. Number of moles is given by mass over the molar mass, that is 6.75 over 58.5, giving us 0.115 moles. Now, 0.115 moles are contained in 452 milliliters. How about in 1,000 milliliters of the same solution? How many moles will we have? We have 0.115 moles times 1,000 milliliters over 452 milliliters. Milliliters cancel out and we remain with 0.25 moles. And because these moles are in 1,000 milliliters, this is the same as 0.25 molar. Another example. How many grams of potassium hydroxide are required to make a 250 milliliters of 6 molar solution? In our solution, first we find how many moles are in 250 milliliters of a 6 molar solution. Molar means the number of moles in 1 decimeter cube or 1 liter or 1,000 milliliters or 1,000 centimeters cube. And so 6 molar means 6 moles are in 1,000 milliliters. How many moles are in 250 milliliters? We have 6 moles times 250 over 1,000, giving us 1.5 moles. Now we convert the moles into mass using the molar mass. Molar mass of potassium hydroxide will be equal to 39 plus 16 plus 1, which is 56 grams per mole. Number of moles is equal to mass over the molar mass. and therefore mass is equal to the number of moles times the molar mass. We have 1.5 moles times 56 grams per mole, giving us 84 grams. Next item, dilution of solutions. Now, when diluting a concentrated solution, you are increasing the volume of the solution, but the number of moles of the solute remain the same. So the initial concentration times the initial volume should be equal to the final concentration times the final volume. M1V1 is equal to M2V2, where M and V represent molarity and volume respectively. What is important is that the initial and final concentrations must have the same units, and the same goes for the initial and final volumes. Let's take an example. How many milliliters of 2.5 molar sodium hydroxide solution are required to make 525 milliliters of 0.15 molar solution? We have M1V1 is equal to M2V2. M1 is 2.5, we don't know V1. M2 is 0.15 and V2 is 525. 2.5 times V1 should be equal to 0.15 times 525. To find V1, we divide both sides by 2.5, and if we do that, V1 will be equal to 31.5 milliliters. Another example, 45 milliliters of 6 molar hydrochloric acid solution is diluted to a final volume of 0.25 liters. What is the final concentration? Next, we look at stoichiometry of chemical reactions, the law of conservation of mass. Now, in the 18th century, scientists thought that when things burned, a substance called phlogiston came out of them. Then, experiments in enclosed vessels where substances could be accurately measured began to help early scientists such as Lavoisier understand that when things burn, oxygen is added. He realized that matter could be changed but not destroyed. In 1789, he established the law of conservation of mass. In chemical reactions, no matter is lost or gained. These experiments on combining weights also showed that elements combine in fixed ratios, the law of definite proportion and constant composition. And they led Dalton to publish his atomic theory in 1808. Modern chemistry had started. By mid-19th century, only half of the elements had been discovered, but enough to enable Mendeleev to produce his famous periodic table in 1869. Chemical equations began to be written as we know them today. For example, the burning of magnesium. This needs balancing. When we balance chemical equations, we are simply obeying the law of conservation of mass. All the atoms in the reactants must be accounted for in the product. It is easy to see this if we draw the atoms rearranging themselves to form the product. You can see clearly that no atoms are gained or lost during a reaction, so the mass is conserved. Here's another example. A reaction you see every time you use a gas cooker which uses natural gas methane. Is this equation balanced? It's easier to count if you draw the atoms and molecules as models. Carbon, 1 each side. Oxygen, 2 to start with, but we have 3. Hydrogen, 4 to start with, but now only 2. To balance the hydrogens, we need to add 2 more hydrogens on the right. To do this, we add another water molecule. The carbon and hydrogen balance, but we have 4 oxygen in the product, but only 2 in the reactants. So we add another oxygen molecule to the reactants. Now we have conserved mass. So the law of conservation of mass simply says that during a chemical change, there is no loss or gain of atoms. It is for this reason that we balance chemical equations.